warm, clear waters of the Caribbean were struck by Hurricane Allen in August 1980, and then again, 8 years later, by Hurricane Gilbert. These were two of the biggest hurricanes ever recorded here. They devastated the corals of this ancient living reef. This is a story of how living systems cope with environmental disruption.
Although hurricanes may seem like rare events in our lifetime, on a geological timescale they're common. And it's part of a natural process that reefs have to contend with and which play a part in the growth of a reef.
This is Dendrogyra, the pillar coral, which grows in clusters of vertical columns. Here's another pillar coral that was knocked down by Hurricane Allen in 1980. But it didn't die. It continued to grow upwards. Between 1980 and 1988, it grew 12 centimeters. That's 1.5 centimeters per year. This big pillar coral was knocked over during Hurricane Gilbert in 1988, just 4 weeks before filming. It was known locally as the Castle, and it was the symbol for the Discovery Bay Marine Laboratory. Jeremy Woodley could now see that the castle itself had grown from an older fallen pillar. Both were built by the same coral organism, which must be hundreds of years old. In contrast, these massive corals survived both hurricanes. But before 1980, they were surrounded by a thicket of delicate branching staghorn coral. This was smashed into rubble by the violent waves of Hurricane Allen. Here's a specimen of the staghorn that survived the storms because it was protected by massive coral on 3 sides. Coral growth helps to create a reef, of course, but it also provides complex habitats for many other organisms. But those other organisms can also be destructive. Burrowing and grazing animals abrade the coral. An amazing 90% of the calcium carbonate fixed by corals is lost as sediment. Here we see a reef, but we can see very few fishes. These reefs have suffered from overfishing, and the fish community is greatly reduced. The removal of fishes has deprived the reef community of important herbivores and predators. There's less grazing than on a normal reef, and because there's less grazing, the algae grow more successfully and may even overgrow the corals. This is the green alga Halimeda. Underneath it are the bleached white tissues of the dying coral. Other important grazing animals on coral reefs are sea urchins, like these diadema. During the 1980s, diadema suffered from a natural epidemic that greatly reduced its numbers. With the fishes gone and the diadema greatly reduced, there was even less grazing and even more algae. A long-term photographic monitoring program was set up here at Discovery Bay to follow changes on the reef. The system is designed to enable photographs to be taken at precisely the same place year after year. In 1976, this frame was mostly occupied by a healthy colony of the massive coral Montastria annularis. In the upper right, an elk-horn coral, Acropora palmata, reaches towards it. 2 years later, The rapid growth of the elkhorn coral has begun to overshadow the slower growing massive coral beneath. In time, the massive coral would have been completely overshadowed and killed, except that Hurricane Allen intervened. The elkhorn coral was completely destroyed and swept away. The skeletons of dead corals contribute to the reef fabric, and storm-damaged fragments are flung up as rubble on the reef flat or onto the shore behind. Leaving Discovery Bay on the relatively undeveloped north coast, we cross to the most densely populated parts of Jamaica, where the environmental pressures are mainly of human origin.
Kingston Harbour is one of the largest natural harbours in the world and is bounded by a city of nearly 1 million people. Almost all of the sewage wastes and other wastes from that city are discharged into the harbour, and the project which we are undertaking here is aimed at studying the effect that the discharge of those wastes into the harbour and then out of the harbour into the open sea here along the Hellshire coast is having on this coastline. The project is being undertaken by a multidisciplinary team of marine scientists from the University of West Indies. And in the end, we hope to be able to give some logical advice on how Kingston's wastes should be disposed of.
Go. We have used a series of standard oceanographic techniques to make these measurements, including current measurements, measurements of temperature and salinity, and have derived equations for density and density flow as a result of these measurements. We have reoccupied a series of stations based on a grid sampling technique and have a long time series of seasonal events in water movement and physical characteristics of the water column along this coastline. Our measurements suggest that during periods of intense rainfall, the water from the harbour flows out of the harbour mouth and is constrained fairly close to the Hellshire coastline. The characteristics of this plume are very clearly defined on the profiles, particularly of salinity, as shown from the CTD data. This profile shows a strong kink, which is identified as a salinity deviation of 2 to 3 parts per thousand, below which the well-mixed bottom waters are defined as a straight line. This shows a CTD profile where the waters are relatively well mixed. As we move away from the harbour mouth and down the Hellshire coastline, the strength of this signature changes and the profile becomes straighter with a less well-defined kink at the upper surface.
Sampling the plankton in the water can help to monitor the influx of nutrients resulting from human activities. Mona Lindo.
We've just been sampling in an area that is suspected of receiving regular inputs of human sewage, which would effectively add nutrients to the water. What we have here is a sample of the plankton, and as is expected, 1 or 2 species will dominate the population. One such species is a shrimp-like animal. It's microscopic and you can barely see it, but it's called Lucifer faxoni, and this guy is known to occur especially in areas that receive nutrients, so he is an indicator of polluted waters.
Preliminary results show that numbers and biomass of zooplankton are greatest at the harbour mouth and decrease towards the open sea.
One of the most obvious environmental problems along the Hellshire coastline is the erosion of the point behind me. We can identify a number of possible causes as to why the erosion is taking place. We suspect that pollution from the harbour is triggering excess growth of weed and resulting in overgrowth of corals, particularly near to the reef crest. As we can see, the bryopsis growth is substantial. The result of this is that the corals are choked and die, many of which are bleached or covered with weed. The breakdown of the coral framework which follows results in a change in nearshore current patterns and sediment transport and the redistribution of shoreline sediments further along the coast. We can identify a number of other problems which are contributing to erosion of the shoreline. They are particularly related to human occupation of the environment, the clearing of trees and shrubs, the grazing of vegetation by animals, and the trampling, particularly by weekend visitors. The grass and shrub and tree cover, which is important for stabilization of the coastal dunes, is being lost, with the result that the prevailing southeasterly onshore winds transport much of this sand inland and away from the shoreline, resulting in shoreline migration.
Where sediment transport has been disturbed by human activities, there's sometimes a biological remedy, involving the transplantation of seagrass.
The techniques of seagrass restoration allow us to go into an area which has been impacted in some way, for instance by dredge and fill activities, and put back in a cost-effective manner what has been taken out. What we're using right now is this particular species of seagrass, which is called turtle grass. This particular species of grass has a very thick root system with finer adventitious roots, basal shoots, and these come up to bear long, flat leaves. What I've just been doing is putting in units like this in a grid system with the hope that given time, 6 or 8 months, it will coalesce to form a mature seagrass bed. A seagrass bed like this one does 3 main things. First of all, this particular species of seagrass has the root system which goes down and forms a bed which is about a foot or more thick. So they act as an extremely important natural erosion control measure for protecting the coastline. Secondly, the long leaves increase the surface area on which other smaller plants and animals can grow, thus providing more food for young fish. These leaves also form a maze system within which young fish can go to hide. So it's very good as a fish nursery. The third function of a seagrass bed is primary productivity. Just like the grass on land, this is our underwater grass, which grows and feeds on the sunlight to produce energy, which can be used by the animals. Behind me, you will see a mangrove area, the seagrass in the water in front of it, and in the distance, the coral reef. Often, these 3 very different ecosystems occur in close proximity to one another. And when they do this, they tend to interact to protect each other. The coral reef protects the seagrass bed and the mangrove by reducing the wave energy that comes in to impact on them, while the mangroves and the seagrass in turn protect the coral reef from effects of land nearby. The mangrove acts like a giant sponge so that fresh water from land runoff doesn't rush straight out onto the reef, while the leaves of this seagrass act like baffles in the water to encourage particulate matter to settle out so that the water which eventually gets to the reef is very clear.
This is an area dominated by red mangrove forest, typical of the seaward side of mangrove swamps. The red mangrove is better adapted to high salinities than any other mangrove species, or indeed any other trees. The leaves are relatively large, and there's a maze of aerial roots extending from the branches and trunks. The substrate is oxygen deficient, and the aerial roots allow atmospheric gases to enter the underground root system. Estimates of mangrove productivity can be obtained from leaf litter traps. Each month, the leaves are collected, dried and weighed. This routine was interrupted just 4 weeks earlier by the passage of Hurricane Gilbert. The storm stripped most of the leaves off all of the trees and damaged many of the larger ones.
It is a common misconception to view mangrove areas as wastelands. However, this is not true because many of these areas act as important nurseries for commercial fish, shrimp, lobsters. The roots also provide an attachment for a number of organisms such as sponges, barnacles, oysters. In spite of this, many of these areas have been reclaimed under land reclamation schemes. This is the seedling in one such area, but where the mangroves were allowed to grow back after they were removed some 20 years ago. It begins with a structure like this. This is a seedling of the red mangrove from which it all starts. It has a growing tip and a root system already in place. It will fall from the tree and establish itself in the substrate. In time it will grow, mature and spread out, and soon this area once again will become a dense strand of mangrove forest.
The bay we're overlooking here on the south coast of Jamaica is called Port Morant. We're actually in an area called Bowden. This bay has surrounding it mangrove stands which have on the prop roots of the mangrove trees growing naturally Crossostra rhizophyri, the local Jamaican oyster. The stock of oysters in the mangrove, the parent stock, usually spawn and produce young oysters twice in the year. The young oysters, after having a pelagic larval stage, finally settle down on some suitable hard substrate. In this area, we establish these rack standing structures, and on these structures we place bits of rubber tire which are strung on nylon or plastic line, and we collect the oysters. After about 4 to 6 weeks, they would have attained a size of about a centimeter. We then remove them from these racks, and we resort these tires, and the oysters which are above this desired size are then hung on longer strings of nylon and are sent to growing areas. Normally the growing period that farmers use is 4 to 6 months. The oysters are then removed manually from the pieces of rubber tire. They're washed and graded and then marketed, usually into the Kingston metropolitan area.
On the north coast of Jamaica, there are many fishermen who fish in their own small boats, sometimes with a partner. The fishermen tend to be in competition with one another. They're fairly individualistic. They may not realize they're in competition with one another, but they're all after the same resource. The fishery here is quite overexploited, and probably they spend too much effort catching the fish they do catch. The fish are small, they don't catch a lot of fish. Take fish pots or fish traps, for example. The larger the mesh on a fish trap, the fewer the fish it will catch, but the larger the fish will be. This is good for the fishery as a whole because it allows the fish to reproduce, allows them to grow to a size where they can reproduce. But the individual fisherman using that large mesh trap loses out because he will catch fewer fish. Morning. I know you've just gone through a hurricane a few weeks ago. How has the hurricane affected the fisherman's ability to fish?
Well, we lose all our fish traps. And some boats have damaged and things.
Some boats damaged too. Yeah. How many fish traps were you fishing at the time?
I have 15, my partner have 12, and he have 6.
And they cost quite a bit of money out here to make.
Yeah, maybe about $200 Jamaican per each.
And most of the fishermen lost their traps?
Every fisherman.
Every fisherman does.
What are you doing about getting new traps?
Well, we have to replace them with our own money.
Yeah, which is scarce.
Very much. Very much.
Money is scarce.
Yes, it is.
Right. There were fewer fish being caught now. How do you explain that?
Well, I think you have too many fishermen now.
As you say, the destruction of the reef is
one. And you have plenty of fishermen too.
Yeah.
Yeah, you have a variety of fishermen fishing in just in 1 year, maybe 2 miles over a period of say 50, 60 years. You know, fish must get less.
Yeah, there has been.
Yeah. Yeah. Fish get less.
Need to explore how far
Deep sea.
deep sea or somewhere.
The Discovery Bay Fisheries Improvement Project is something of a departure from traditional fisheries management procedures. Instead of telling the fishermen what they ought to be doing or what they must do, we're hoping to help the fishermen by having them report their own data on the numbers and kinds of fish that they catch and on their costs and the revenues that they get from those fish. Then we should be able to use that information to assess the biological stock by combining it with our surveys of the fish, and also by analyzing their economic data, give them feedback about what their real costs and profits are, and help them make sounder economic decisions. In the long run, we hope that we'll be able to pull the community as a whole together to make decisions that are rational for the fishermen as a whole, rather than simply for the individual fishermen.
The management of local fisheries on a sustainable basis is just one example of the approach needed if Jamaica's marine environment as a whole is to thrive. Mangroves are another example. In addition to their biological role, they can yield a steady supply of wood for charcoal production, if they are not destroyed by other activities. Research and monitoring provide the data needed to balance development with conservation. The aim is to protect the environment from overexploitation, whether of its commercial resources or simply its beauty. But the pressure of sheer numbers can damage the coastal zone. The marine environment is a living resource, part of the island, part of its culture, part of its economy. Something to be managed for the benefit of all, and something to enjoy.
And